All right, here we're going to be talking about symmetry. So there's two types of symmetry that we're going to be concerned about: reflectional symmetry and rotational symmetry. And really all it means is that after the reflection or after the rotation, we end up with the exact same shape and orientation that we started with. So a figure has reflectional symmetry if the pre-image and the image are the same after the reflection. Each point has a matching point on the other side of the line of reflection. So line of reflection is also sometimes called the axis of symmetry. Especially when it's horizontal and vertical. But either way, we're thinking about flipping half of the image over the line, and it flips onto the other half of the image. So, looking at these four pictures, we're trying to think about all the lines of symmetry that we have. Actually, these should be marked as congruent. This is really a rhombus. It might be visually clear, but it should be marked for clarity that those are congruent. Actually, same thing with this pentagon. That's a regular pentagon, where all of those sides are the same. So you can see that we have a horizontal line of symmetry. The top triangle would flip directly down onto the bottom triangle if we reflected over that line of reflection. So we have a horizontal line of reflection, and we have a vertical line of reflection. It could also flip from the left side to the right side. So we have those two lines of symmetry. You might be thinking maybe we have a line of symmetry cutting from one side to the other, like from the midpoint of each side. That doesn't actually line up perfectly. Like this point, flipping over to the other side, it really wouldn't land on top of that. So we really just have those two lines of symmetry. The New Orleans Saints logo has one line of symmetry just cutting straight down from top to bottom. Every regular polygon has an easy way to figure out how many lines of reflection it has. So for this pentagon, we can go from one vertex across a shape through the middle of the other side and create a line of symmetry there. That point would flip over the line of reflection onto that point. This one would flip over and land on that point. That's going to be true of each vertex. You can go from the vertex to the opposite side, and each one of those is going to be a perfect line of symmetry. So a pentagon has 5 sides or 5 vertices, and it also has 5 lines of symmetry, a regular pentagon, when all the sides are the same. These lines of symmetry also pop up in nature. This isn't going to be perfect, but a vertical line of symmetry could be passed over that butterfly, and you can see, like in nature, it's not going to be exactly matching up, but these points will generally match up with the opposite side. So it does actually pop up naturally in the world. All right, I want you to try to find all the lines of reflection that you see on these figures. All the lines of symmetry that you see on these figures. When it says vertical symmetry for these letters that you're trying to sort, that means it has a vertical axis of symmetry. For example, the letter T has a vertical axis of symmetry. You kind of missed the middle, but you can see that it would flip from left to right onto either side, so that has vertical symmetry. You can see the letter C has horizontal symmetry. That horizontal line, at least it's pretty close. The way that font's written, the top part of that C is a little bit different from the bottom, but really it does match up directly. That point would flip over that horizontal line of symmetry onto the other side. So C has horizontal symmetry. The letter O has both. So you'll put that in the middle of the Venn diagram, showing that it has both vertical and horizontal symmetry. All right, now we're going to get to rotational symmetry. Same exact fill in the blanks here, really. If the pre-image and the image are the same after a rotation, then it has rotational symmetry. And we're going to describe this by the angle of rotation. So how many degrees we can rotate it by to get back to the same shape. Every shape can be rotated 360 degrees and end up back where it started. So every shape can be rotated by 360 degrees. We are then going to decide degrees that are smaller than 360 if it actually can be rotated by that number of degrees and end up with the exact same shape and orientation that we started with. So you can see with the letter Z, we flip this upside down, or halfway, or 180 degrees. That would end up exactly where it started. So this has two angles that we can rotate it by, 360 and 180. And that's it. The recycling symbol. Actually, you can pretty much just follow the arrows. Going from this arrow, you can flip it over a third of the way, and another third of the way, then another third of the way. 1/3 of 360 degrees is 120, so it can go 120, another 120, and then another 120 to end up back where it started. So we can rotate it by 120. Those two together would be 240. And of course, we could rotate it 360 degrees. So that has three angles of rotation that we could rotate it by to create the exact same orientation. Regular shapes always have this same kind of formula, just like they do with lines of reflections. Going from there to there, then from there to there. You're going to be able to do this 5 times because it has 5 sides and 5 vertices. So we're really just going to divide 360 by the number of vertices or sides that it has. So each of these is going to be 72 degrees. So we can rotate it by 72, or 2 of those would be 144, or 3 of those would be 216, or 288, and of course we could also do 360. So it can be rotated 5 different ways to create the same orientation. The New Orleans Saints can't be flipped upside down. It can't rotate by anything besides a full turn around, which is 360 degrees. All right, so that's the angle of rotation that we could use to describe that symmetry. There's a couple of specific details that we got to get into here. Point symmetry refers to if a figure can be flipped upside down if it only has, if it has 180 degree rotation as a rotational symmetry. So point symmetry is a subset. Things that have point symmetry have rotational symmetry, but not everything that has point symmetry has other kinds of rotational symmetry. It might just have 180 degrees, or it might be 180. It might also include 90 and 270. There might be other ones included, but we say it has point symmetry if it can be rotated by 180 degrees, basically just flipped upside down and end up with the exact same shape. The order of rotational symmetry describes how many different rotations we can do within 360 degrees. So it's really just counting how many rotational symmetries we have. Everything has an order of 1 because it can be rotated by 360. It's either going to be 1 or more. This has an order of 2. This has an order of 3. This has an order of 5. This has an order of just 1. We're just counting up the different angles that we can rotate it by to create the exact same image. 2, 3, just the number of angles that we have that we can rotate it by under 360 degrees. All right, so here we're going to try to state the order of rotational symmetry for each figure. So a square is a regular quadrilateral with 4 sides. Each corner could rotate to any other corner. 1, 2, 3, 4. Each of those is 90 degrees, but that's actually not even what we're asked there. We're just asked how many times that can be rotated. Well, that's 1, 2, 3, 4. The order is 4. A regular 40gon, which means it has 40 sides and they're all the same, follows the exact same formula. This has 4 sides. That's a regular quadrilateral. It has 40 different degrees that we could rotate it by, or each one would be 9 degrees to end up with the exact same orientation. Here we have a number 3. We have a rectangle where we have diagonals drawn. So we could rotate from here. If we rotate that 90 degrees, it really won't have the same orientation. It'll be standing upright. So 90 degrees actually doesn't work. But we could flip it halfway, where this point would flop over to that spot, and then we could flip it the rest of that. We could rotate it 180 degrees, and then 360, giving it an order of 2. The next one is a regular pentagon with a star in it, which is actually called a pentagram. We have the exact same order as we would for a normal or regular pentagon. You can imagine the star rotating also by these 72-degree rotations. So that has an order of 5. All right, try to figure out the order of each of the figures on the next page.